Data Center Transformation 2025. I'm joined by Nathan Woollett from TreQ. This is fantastic. So I've already had two people from the small nuclear energy come along to me. Now I've got my second person from quantum computing, but you're a very, very special guest. But first, tell me a little bit about what you do within TreQ as such.
Cool. So so I'm the principal engineer at TreQ. So I kind of touch on all parts of the business. Primarily at the moment, my focus is on the hardware development as well as the facility and infrastructure build out. But one of the long-term goals that I'm working with, within the company, is the productionization of quantum computers. Quantum computers are still coming out of research and development labs. They're not quite ready to go into production workloads, into real data centers, and they're not quite there yet. And so there needs to be a lot of process and thought put into how these systems are engineered, how resiliency is put into them, and a way that we can actually guarantee when a quantum computer is delivered to your site that you can actually start using it.
Right. That's going to lead me to a question that I wasn't going to ask, but I'm going to ask it now. What sort of timeline are we looking for that?
So we aim to have a system on site with you within 6 months. Frankly, at the point of development we are right now, there will be a small amount of bring-up time involved with that, several months probably. One of the things that we aim to do, though, is to bring that down even further. Compared to a lot of companies, though, I genuinely, in a previous job, was talking with one of the full-stack providers, and I was trying to partner with them on a project, and they told me it was going to be 2 years to delivery. 2 years to delivery is just not something that we can build an industry on top of. So having this kind of get it into your site, getting it operational, and then as TreQ, what we're also doing is putting together a development pathway. And so over the next 2, 3, 5 years, we can upgrade your infrastructure so that your compute capability improves, and you can stay up to date with the latest and greatest as it comes out of quantum.
Wow. Now, I was told that you hold quite an accolade within the industry. You were one of the first people, or the first person, to commercially develop a quantum computer.
Yeah, that's right. So I joined a company called Rigetti. They were one of the early superconducting quantum computing startups. Came out of Silicon Valley, actually. So they were setting up operations in the UK. They needed somebody who's got a lot of experience setting up quantum computing labs, building systems, things like that. Thankfully, that was my background, and at the time I was actually living out in the US and wanted to move back to the UK, so there's fortuitous circumstances. So I joined Rigetti. We worked at the site of Oxford Instruments, who's one of the key suppliers of those dilution refrigeration systems. Mm-hmm. So they're the gold chandeliers that you think of as a quantum computer. So we worked on site with them, and we built out a Rigetti 32-qubit device, which was then available on the cloud. So real researchers from Standard Chartered, as well as a select number of universities, were able to then access that system and start running kind of R&D processes on that system. So we believe that was the first commercial quantum computer in the UK.
So this is awesome for me, because I could be sitting in the presence of the Tim Berners-Lee of quantum computing in the UK.
I mean, yeah.
I love the modesty, love the modesty.
It's one of those things where we really see our jobs as... nothing I do is particularly... Sorry, touch the microphone. Nothing I do on a day-to-day basis seems that crazy to me. It's putting cables in, it's doing calculations, it's doing measurements. It's kind of what you're trained to do as a physicist. Mm-hmm. It's only when you talk to people like yourself and people who aren't ingrained in the real detail of what we do that you see, we are at the foundation of a new part of, it's a new industry, but also a new part of the data center, the compute industry. It really is at the start of it. So it's kind of fascinating. I think my wife appreciates that more than I do, to be honest.
I think we all do, actually. So that leads me on nicely to my next question. As a complete layman to the quantum world, to the quantum computing world, explain to me exactly what quantum computing is, if you can, and how's it going to benefit us in the sort of near future? Well, what are we going to see as the general public?
Yeah. So quantum computing is incredibly complex when you want to get into the real detail of the quantum system. But the guys at the office always laugh at me because I have this adage: there is no such thing as a quantum computer without a classical computer on either side. If you take away that classical computer, all you've got is a really cool physics experiment, which is why I work in this field. So what you actually are doing is you're taking a classical problem, you're converting it in a way that it looks like a quantum system. So that quantum system may be a square grid superconducting lattice. It may be an arbitrary grid neutral atom lattice. It might actually be a selection of electrons that are living in quantum dots on a silicon chip. What it looks like doesn't really matter too much. You're just adapting your problem over to it. You are then using these quantum systems. So an electron on its own is a quantum system, as your computational unit. So electrons have a property called spin. So they can be spin up, they can be spin down. And if you do certain operations on them, you can put it into what we call a superposition between the two. So it's kind of like being in spin up and spin down at the same time, with a probability of where it will fall on the two. But whenever you measure it, you always get one or the other. What this means is you've actually got a way of encoding your data in a more complex manner, which means that you can do different sets of mathematics with it.
Right.
So that's kind of at the core of what a qubit is. The way it impacts us is if you look at the ability to process information, the amount of information you can get in a quantum computer goes as 2 to the n. There's 2 to the power of the number of qubits you have. So for every single qubit you add, you double the amount of computational space that you have. So this means that something relatively modest, 20 qubits, I can just about simulate on a classic computer. When I get to 40 qubits, I need an entire data center to simulate how that system is working. Now, when we talk about a production size quantum computer, we're talking tens, hundreds, of thousands, millions of qubits. And so the actual computational space that you have available to you to run problems is enormous. And so you've got that side of it where you can really have these high throughput processes. But the other side is optimization and you're finding minima. So you actually can set up your problem such that your data, such that your search for your data is a quantum mechanical process. And so if you're looking for an optimization right now, normally what you do is you set it up so you're finding the minima in some distribution. Well, what happens if your minima is here and then there's a drop off on the other side and you've got a little your classic, your gradient descent, these kind of classical optimization techniques can get stuck in what we call a local minima, or something like a barren plateau, which is where it looks flat for a long way. A quantum computer, because of the way that you can split the data, split the process across a lot of data, avoids that. You will always have a probability of finding that lowest solution. So when you find and are certain you have a solution with your quantum computer and optimization, it is the best optimization for it. I think it was in the presentation I gave today, which I absolutely love, is one of my colleagues at a former job told me how Deutsche Bahn, the German train network, they run their optimization for their scheduling for a set amount of time, call it 6 hours. They run it for that long, and whatever they get out at the end of it, that's good enough. And if anybody used the German train network, they'll know it's not good enough because they're notorious. That's the kind of problem that we'd like to be able to solve with a quantum computer.
Wow. Okay. That's awesome. Right, last question. How have you found today's event?
Absolutely brilliant. It was, I came out of academia into kind of the industrial side of quantum computing about 5 years ago. And I very quickly realized that actually we were all at that time very much talking to other quantum people. So I've really made it an effort over the last few years to get out and start meeting people in the data centers, because ultimately this is where our technology needs to go towards. So being able to talk to people who are hosting data centers, people who are using data centers, people who are producing parts for them as well, so that we can start aligning how a quantum computer will fit into that is brilliant. And I think this kind of event is the only place you get that full cross-section of the data center community.
That's awesome. Listen, Nathan, thank you so much for your time. Enjoy the rest of the day.
Awesome.
I hope to speak to you again soon.
Awesome. Thank you, Mark.